Swayam Prabha. Digital India. Educated India.
What we saw in the last class was how the Nusselt number, which basically is a measure of the dimensionless heat transfer, is dependent only on Reynolds number and Prandtl number. What we did is we made the momentum equation dimensionless. That gave the velocity as dependent only on the Reynolds number, and the temperature was dependent on the Peclet number, but Peclet number we prefer to write it as Reynolds number and multiplied by Prandtl number, because Prandtl number is decided by the fluid properties, and Reynolds number depends on the velocity only. So, when I change velocity in an experiment, I can study the effect of how Reynolds number is affecting the correlation. That was the idea. Okay. So, I think you had a question, what about the pressure, correct? What about the pressure drop? So, I mean, just think of this problem. So, when we made the flow past the sphere, okay, we analyzed the creeping flow, okay. I mean, just to give you why the pressure drop is not coming into the picture. In the creeping flow limit, we have done this problem. What we did is we converted the flow field in terms of the stream function. You got e power 4 psi equal to 0, and we solved for the velocity, okay. So, we solve e power 4 psi equals 0 and get velocity, that is the Vr and V theta components, okay. And this will depend upon u infinity, the far upstream velocity, if you remember, okay. This is dependent on u infinity, the far upstream velocity. And I mean, we got this done earlier. We derived the equations for the velocity field Vr and V theta, okay. Nowhere in this calculation the pressure is coming up, because you eliminate the pressure in the formulation, okay. So, here pressure does not appear, and as far so the velocity field can be calculated if you know the fluid properties and if you know the far upstream velocity. So, that is the only thing you need to know, and the surface, okay. So, basically Vr V theta can be found, and this is used in the energy equation to find the temperature, okay. That is what we are doing. We just find the Vr V theta from the momentum equation. I mean, the process was we converted it to stream function and all that. So, this does not have anywhere in the calculation, pressure does not happen, does not arise. So, you do not need to independently specify the pressure. So, the velocity field is in some sense independent of pressure, especially if you are looking at liquids, okay. If you look at compressible effects, then compressible gas flowing, then you may have to consider effect of pressure. So, as long as things are incompressible, you do not need to worry, okay. But if you want to calculate the drag force, then the pressure comes into picture. So, you remember the drag force, we had two contributions, one because of the viscous drag, one because of the pressure component. So, because we are only interested in the heat transfer problem which has only the velocity, so we can do the calculation without having to worry about pressure, the effect of the pressure. Okay. So, that is the, I mean yesterday I gave you a very short answer, but I thought I should spend some time and explain to you why the pressure does not come. Okay. So, here but so for heat transfer and an incompressible liquid or fluid, liquid flowing, okay, pressure effects are not there, but if we have compressible flows, then pressure has to be considered. Okay. So, that is the whole idea. So, I mean that is because then depending upon the pressure, the compressibility, the density etc., will change, and you are going to have to take into account density variations. For example, right now I told you we are not considering any variation in the properties, although we are solving a heat transfer problem and density is a function of temperature, density is a function of viscosity is a function of temperature, we are taking all the the properties as constant. So, since we take all the properties as constant, we do not need to worry about compressibility effects. Okay. So, I mean all these are subtle points that are connected. So, that question was actually a very good question as to what happened to the pressure. Okay. But I think this is what you have to do, you have to think. I mean it is not just writing an equation and solving, you need to sit down and think about what is the assumption you have made and how consistent you are, how inconsistent you are, and things like that. Okay. So, this thought process is what you have to develop. Okay. So, but if you are focused on drag force, then for drag force calculation, pressure has to be included. Okay. That is the thing. So, I hope I am clear. So, you should go back and look at how we solved the creeping flow past the sphere. You will see that pressure does not show up. So, I mean you can actually get the velocity field without the pressure, and the reason is because we are assuming incompressible. Okay. If it is compressible, then pressure is important, and then you need to one more dimensionless number may come. Okay. And that is that. The so for heat transfer, there is no contribution from pressure effects, since we assume all properties are constant independent of temperature. Okay. So, the other question which I want to talk about is another question at the end. What about the temperature distribution inside the solid? We are talking about flow over a body, okay, and we are talking about the rate of heat transfer. So, as far as we are not really worried about what is, so whatever we derived by way of Nusselt number, by way of the temperature profile, was only the temperature profile in the fluid. It was not the temperature profile in the solid, right. I wrote the energy equation, but that was for the fluid. I did not write the energy equation for the solid. Okay. So, the temperature profile we obtained was for the fluid when the body was at constant temperature. So, actually the body surface was at constant temperature. We are saying we are doing something and the surface was temperature at the surface. So, we didn't bother about what is happening inside the body. Okay. So, you need to get that clarity. So, we are saying there is a body, let us say a sphere at a constant temperature and liquid is flowing. We wanted to calculate the liquid profile. So, for that we solve the energy equation. Okay. So, the temperature profile, the temperature we solved for was of the fluid. I mean, I have a sphere, this is at some T0 and you have some liquid fluid flowing around it, okay, T infinity, and this in this outside liquid, outside fluid is where we have the energy equation. Okay. So, when we spoke about finding the flux at the surface, I spoke about calculating the derivative of temperature in the normal direction, okay, dt dr, dt dn. So, that dt dn is being calculated on the fluid side. It will be equal to whatever is there in the solid side, but I am not interested in the solid. The flux at the surface on the fluid side will be equal to the flux on the solid side. Okay. But since I am not interested in the solid for this particular problem, since the temperature is fixed, I am only interested in what is the heat loss from the surface at temperature T0 to the fluid. Okay. So, the temperature gradient to find the heat loss is on the fluid side. Okay. The thermal conductivity that you will use when you use minus k del theta dot n is on the fluid side. So, K F is the okay, and this is opposed to what we did earlier when we had this problem of a solid sphere. In the solid sphere we said we are interested in how the sphere is cooling down. So, then you are interested in the temperature profile inside the sphere, where we were talking about the thermal conductivity of the solid of the sphere. Okay, we wrote the energy equation for the sphere and then we have this external heat transfer coefficient and then we had. So, there we were equating what is the heat flux inside the sphere with what is the heat flux outside the sphere, the temperature profile. Okay. So, there you had K of the solid. Okay. So, in that earlier problem which we did a few lectures ago, if we spoke about this earlier problem, right, in an earlier problem we focused on temperature as a function of R and T in the sphere. Our objective was how much time does the sphere take to cool, okay. Then here the Ks, the solid thermal conductivity comes into picture, okay, and you again had a dimensionless group Hd by K, and here Hd divided by Ks, which is your Biot number, is heat transfer by convection in the fluid to heat transfer by conduction in the solid, okay. So, that was that problem that we were looking at. But when I am talking about Nusselt number, both our numerator and denominator are in the fluid, okay. For Nusselt number, and this is also Biot number, which is also Hd by K, but the case of solid, for Nusselt number it is Hd divided by Kf. We will see this, okay. This is heat transfer by convection in the fluid divided by heat transfer by conduction in the fluid. So, basically what Nusselt number does is, I mean, it tells you, supposing you have a liquid, a sphere in a stationary liquid, because the liquid is stationary, the fluid is stationary, the only mechanism of heat transfer is going to be by conduction, because you are neglecting or density change and all that, no natural convection, okay. So, then you have only the conduction, but now conduction is a slow process. So, you want to try to make it faster. So, you know make the liquid flow around it, around the sphere. So, heat transfer will get increased. So, Nusselt number is a ratio of that, okay. When you have convection in the fluid and when only conduction in the fluid, what is the ratio of the heat transfers? Whereas in Biot number is, you can change the convection in the fluid to what is the conduction in the solid. So, that is a subtle difference. One basic thing is, this is you use thermal conductivity of the fluid here, this heat transfer is the same, the length scale will be possibly the same for both the problems, both the systems, okay. So, you need to, I just thought I should spend some time explaining some of these things. Now, what I want to do is, I want to calculate what is the Nusselt number. I mean, this is a very classical result for a sphere in a stationary liquid, okay. So, there is a sphere at a high temperature T naught. Is this clear? Any questions? So, we have a sphere, okay, that sphere, okay, and we have a stagnant fluid. So, the stagnant fluid. So, what is the rate of heat transfer? I want to calculate what is the rate of heat transfer in the fluid. So, what is the rate of heat transfer in the fluid? That is what I want to know. I am saying the temperature on the surface is T0, far away it is T infinity. So, let us say T0 is more than T infinity. So, temperature as you go in the radial direction, temperature will decrease from T0 to T infinity, okay. So, as you go in the radial direction, you start at T0 and it will go up to T infinity, Okay, that is a qualitative sketch that I have drawn. We want to find out what is the actual graph. This is qualitatively how it looks. Okay. So, if you want to find out this temperature is a function of r, because nothing is changing, okay, and it is symmetric in the theta and phi directions. So, we are going to just solve the energy equation. The energy equation in the fluid here, okay, because there is no velocity and we are looking at steady state, the left hand side becomes 0. So, let me write it down, rho Cp dt by dt plus u dot del t plus k del square t. Okay. There is no source term, there is no, because the temperature again same problem, boundary temperature is fixed, far off temperature is fixed, and because it is stationary and at steady state these two go to 0. Okay. And this is stationary. So, what am I left with? Del square t, but if I say it is independent of theta and phi, del square t depends only on r. Okay. And I have, so basically the equation is 1 by r square d by dr of r square dt by dr equals 0. Remember, we are talking about the fluid. Okay. So, now what does this mean? This has to be constant, r square dt by dr must be equal to a constant C1. Okay. So, dt by dr is C1 by r squared. So, again integrate this, okay. So, like something like a hyperbola, right, rectangular hyperbola decreases with r. Put the boundary conditions, r tends to infinity, temperature equals T infinity. So, C2 equals T infinity, and at r equals r, temperature equals T naught. So, I have T naught minus T infinity equals minus C1 divided by capital R. So, in this case I can write the solution as T minus T infinity divided by T naught minus T infinity. What am I doing? I am just dividing this equation with this equation. Okay. T minus T infinity divided by is equal to R by R, is it? Okay. That is what I have. So, I mean I am just substituted this, you can do it whichever way you want. So, this is my temperature profile. This is, remember, just to be clear, I am putting Tf to relate the fluid temperature. So, in this particular problem, my temperature profile has been found out, and I am going to calculate the rate of heat transfer from this. In this problem, of course, there is no convection, only conduction is there. Okay. So, what is the actual rate of heat transfer? Is minus K fluid dTf by dr times 4 pi r squared, and this has to be evaluated r equals r. Okay. So, this is your now I can calculate dTf by dr. What will I get? R to the power minus 1 bar squared this will give me Kf, substituting the expression for Tf here, bar squared. What is dTf by dr, man? Okay, this is minus, what did I do? There's a minus here, no? This is equal to minus, okay, minus, yeah. So, this is equal to what? Kf T naught minus T infinity times 4 pi r squared by r. Okay. And this is the numerator which I am calculating from the derivative, okay, and the bottom, the denominator, of the Nusselt number is given by Kf times a length scale times T naught minus T infinity times 4 pi r squared. Okay. So, now the Nusselt number is the ratio of these two guys, ratio of, this is the numerator, okay. The numerator, remember, is evaluated as a gradient of the temperature field. So, in this case I calculated the temperature field to show you what it is, okay, because it is a straightforward problem. Once convection comes, then it becomes more difficult to find the temperature field. Anyway, so here Nusselt numbers, this divided by that. So, Kf times T naught minus T infinity times 4 pi r squared by r divided by Kf times T naught minus T infinity times 4 pi r squared divided by length scale. Okay. So, what I have is tuck, 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 everything goes off except Ls by r remains. And if I choose the characteristic scale as a diameter, okay, if Ls is equal to diameter, which is 2r, then I get Nusselt number equals 2. Okay. Now, this is a very classical result, you must have seen it in your BTech in your course. Only thing you have to understand is this is the lowest possible value you can have of Nusselt number. Now, why is this important? Because supposing you are doing some calculation, and if you are in the calculation you get Nusselt number is less than 2, then you got something wrong, because definitely there is heat transfer by conduction. Okay. If only conduction is there, you have Nusselt number as 2, but if there is heat transfer also, convection also happening, you will only have more heat transfer. So, Nusselt number has to be higher. Okay. So, Nusselt number necessarily has to be more than 2, that is the conclusion here. So, now what we do is write Nusselt number as, like I said, rate of heat transfer by convection to rate of heat transfer by conduction. Okay. And so, for any body you write the rate of heat transfer by conduction as HA times T naught minus T infinity. I mean, that is your Newton's law of cooling, the heat transfer coefficient we write as heat transfer coefficient multiplied by m multiplied by delta T, okay, which you can put in your boundary conditions to solve. And this is by conduction will be K fluid times A times the gradient, which is T naught minus T infinity by a suitable length scale. Okay. So, this is the denominator, you have only conduction, therefore, it is going to be given by temperature gradient, okay. And of course, T naught minus T infinity, you can't have infinity at the bottom, because then it will go 0. So, you choose a length scale here, and what you get is H times Ls by K fluid. So, this is how your Nusselt number is defined, I mean this is how I would use it, okay. So, you calculate Nusselt number as a function of rate. So, for a given problem, we find Nusselt number as a function of Reynolds number and Prandtl number, okay. And from once I know the Nusselt number, if I know the fluid thermal conductivity, if I know the length scale, I can find the heat transfer coefficient. So, that gives me a measure. So, if Nusselt number, how far away are you from 2, the heat transfer is better, okay. So, that is the idea. Now, I want to talk about the analogous mass transfer situation. Okay. Yeah. So, imagine there is some sphere again, okay, and then there is some fluid flowing, and maybe it is some volatile compound, or maybe it is something which can dissolve in the liquid. So, there is mass transfer occurring from the surface, okay. And what we want to do is, we want to find out the rate at which this dissolution is taking place, the rate at which this volatilization is taking place, okay, this is a mass transfer. Now, in order to do that, you will talk about the species, okay, which you are interested in. So, I want to point out that there is a very subtle dissimilarity between the mass transfer problem and the heat transfer problem, okay. And I am going to focus only on single solute mass transfer. We are not going to talk about multiple solutes, because single solute itself, once you understand it, if you want to, you can extend it to multiple solutes, okay. So, there is a subtle difference in the heat and mass transfer situations, and we focus only on single solute. Mass transfer. Multiple solutes, you can do it, it gets more complicated, okay. So, now once you understand the subtle difference, then you will be in good shape. But before we talk about all this, I am going and let me tell you what the subtle difference is. So, although we are assuming the properties are all constant, there is no natural convection, okay, no density differences. In the case of mass transfer, there will be a velocity which is induced in the mass transfer process. So, in the heat transfer process, when you say all the properties are constant, I mean there is no mass transfer, no velocity induced, okay. Here, this is a subtle difference. So, what is the subtle difference? even if the properties are constant, we have a velocity generated. Okay, that is it is not because of natural convection. Okay. So, in heat transfer we assume properties are constant, density is constant, we did not have any natural convection, only forced convection. Here even if you have a stagnant liquid like we had earlier, there will be a velocity which is induced, and that is what we have to see, that is the subtle difference. Okay. And we will see how that subtle difference happens, but before that I want to do the analogy of writing the species balance equation, because we solve for the temperature field in the fluid. Again I want to solve for the concentration field in the fluid, okay, because that is our basis, right. So, here, but before we discuss this, let us see the species balance equation in the fluid. Okay. So, we would have dCi by dt plus u dot gradient of Ci equals d del square Ci. I mean I am neglecting generations, source terms and all that. Okay. Terms etc. And remember again this is for the fluid. Okay. This is Ci, concentration of the ith species in the fluid. So, now I mean I am not going to how do you find the u velocity? Properties are constant. Okay. So, u remember is a function only of Reynolds number, same as what we did for heat transfer, okay, because properties are constant. Okay. But what about the concentration Ci? Again, okay, let us do something. C0 is on the surface, C infinity is the concentration far away. So, just like I had T naught and T infinity, temperature of the surface and temperature far away, I am saying this is C0 is the concentration of the solute. Okay. C0 or C is concentration of the solute where you have the mass transfer occurring. So, now again just to keep say steady state problem, we look at and u dotted gradient of Ci equals d del square Ci. Okay. And you make it dimensionless because I want to get like we did last time, I want to make it dimensionless. Okay. We make this less, and I am going to call this C minus C star is equal to Ci minus C infinity divided by C naught minus C infinity. I am talking about mass transfer occurring from the surface to the ambient. Okay. Same thing what we did for temperature. Because this equation is linear, the C naught minus C infinity will come out here, C naught minus C infinity comes out here, and they will cancel off. Okay. So, that is the idea. Now, when I make it dimensionless, I will get U characteristic times U star. U has been made dimensionless as U star, so it is U characteristic multiplied by U star dotted gradient of C star, let us say C star, yeah, C star. So, what comes out here is C naught minus C infinity, and del has been made del star. So, one length scale comes out, okay, one characteristic length comes out, and I have di is a constant, and concentration is made dimensionless C star divided by L characteristic squared. Okay. So, what have I done? Just reduce everything to dimensionless, okay, and I get this. What do I get? This cancels, and I have UCH multiplied by LCH by D, the diffusion coefficient, times U star dotted del star C star equals del star squared C star. Okay. This guy here is like a Peclet number, but this is Peclet number associated with the mass transfer. So, I am putting PEM. Last time I put PH because it was heat transfer, and I had the kinematic and thermal diffusivity DI. This is the diffusion coefficient. Okay. So, this is a Peclet number. So, basically what it means is that this concentration profile depends upon, so C star is a function of Reynolds number. Why is it a function of Reynolds number? Because U star is a function of Reynolds number. C star depends upon U star, which depends upon Reynolds number. It depends upon Peclet number, no, Peclet number mass. Okay. What I am saying is, I mean, there are subtle points. People use Peclet number, you need to know if it is a mass transfer problem, you will use diffusivity. If it is a heat transfer problem, you will use thermal diffusivity. Okay. So, depending on the situation, and again, if we change U in an experiment, okay, both RE and PM change. So, this is not good, because then you are trying to study the effect of, suppose you are doing an experiment and you want to find out how does this thing change. You want to plot your results in dimensionless form. Okay. You want to plot your results in dimensionless form, because that is what is useful for other systems. You do not want to plot your experiments, your results only for your system. So, then all your data will have two parameters changing, Reynolds number and Peclet number. So, you want to avoid that, and so what people do is they will write Peclet number mass as Reynolds number times Schmidt number, where this is U characteristic by L divided by nu times nu divided by D. Okay. So, now clearly this depends upon Reynolds number, and the Schmidt number depends only on the fluid properties. Okay. So, exactly whatever we did earlier. So, instead of Prandtl number, you have Schmidt number. There is only one fundamental difference, because diffusion coefficients are much lower than thermal diffusivity. The Schmidt numbers are much higher than Prandtl number, maybe 10 times or 100 times higher. Okay. So, I mean, you have to look at this, but the diffusion coefficients are lower than thermal diffusivity. Schmidt number, suddenly got a doubt, Schmidt number is SC, no, yeah, Schmidt number will be more than Prandtl number in problems. Okay. So, that is and usually about 10 or 100 times whatever depending upon the particular problem. Okay. That is something we have to remember. Okay. I do not remember these numbers what they are for liquid and fluids, but the argument as to why we are using these two. Okay. So, let me just talk to you and then we will discuss that in the next class. So, what is the subtle difference? So, my point is that we spoke about single solute mass transfer, right. We said we will talk about single solute. That means, what does it mean? There is a solvent and a solute. Okay. So, when you have a mass transfer, there is going to be a gradient of the, and how are they normally expressed? The concentrations can be expressed as a, let us say, mass fraction or mole fraction. So, basically the sum of these two will add up. Okay. Now, if there is a concentration gradient of, let us say A, let us say A is the solvent, both of them start with S. So, A is the solvent and B is solute. So, there is a concentration gradient of A because of which the mass transfer is occurring. Okay. If there is a concentration gradient of the solute, there has to be a concentration gradient of the solvent also because the mass fractions have to add up to 1. Okay. You did not have this situation in heat transfer. So, but this solvent is not going to penetrate. So, the net flux of the solvent is going to be 0. So, you have a concentration gradient of the solvent and the only way it can there can be no net fluxes if there is a convective term where the velocity and the convective flux and the diffusive flux balance. So, what this means is there is going to be a velocity which is induced because of the concentration gradient in the solvent. We will see this again in next class, I am going to do this in detail. Okay. And so, although properties are constant, a velocity is induced and therefore, this is also going to the velocity is going to also contribute to the mass transfer of the solute. Okay. So, you will have a contribution to the mass transfer from both convection and diffusion. Most of the time what we do is we neglect that contribution from convection and we say only diffusion is there. Okay. And then we proceed. So, but if you really want to do it properly, because there is a small contribution to this diffusive mass transfer from the convection, and today people are talking nano and where everything is very, very small. So, maybe that small contribution of mass transfer can be significant at those scales. So, you may not have, you cannot neglect that. But if you are having a bulk system, you may want to neglect it and go, it does not matter, it is only contributing 0.5% to my mass transfer, I do not care. Okay. So, we will see this tomorrow.